continuous groups. Let us start with an example. Consider a 3 by 3 matrix which we denote by RZ of phi, having the following form. So we have cos phi sin phi 0 minus sin phi cos phi 0 and 0 0 1. And we allow the variable phi to take values in the continuous range 0 to 2 pi. Then we consider the set of all such matrices R is at phi, where phi varies from 0 to 2 pi. And we see that these set of matrices form a group under matrix multiplication. To see this, we can consider two such matrices R is at phi 1 and R is at phi 2 corresponding to two values of the parameter, which we denote by phi 1 and phi 2, and use this form of the matrix and multiply R is at phi 1 and R is at phi 2 and see that it is in fact is a matrix having the same form with the parameter phi given by phi 1 plus phi 2. So R is at phi 1 plus R is at phi 2 is R is at phi 1 plus phi 2. So closure property will be satisfied. And all other properties required for a group is also satisfied. So we see that this set of matrices forms a group, and every element of that group is parameterized by a parameter called phi, which takes values from a continuous range from 0 to 2 pi. And such a group is called a continuous group. So in general, a group whose elements are parameterized by a set of parameters, at least one of which varies continuously over some interval, is called a continuous group. And the number of continuous parameters in the set of parameters is called the order of the continuous group. And in this example, there is only one parameter phi, which is continuous, and therefore the group is a continuous group. And since there is only one continuous parameter, the order of the group is also. In general, we may think of an n parameter group where the elements of the group are parameterized by n parameters, which may call as x1, x2, etc. up to xn. And we may write it as an ordered set x1, x2, etc. up to xn. And we may use a simplified notation for this. So this ordered set may be represented by x, which means it's a set of n values x1, x2, etc. up to xn. Now for each value of each set of values of these parameters, there will be one group element. So that means there is a one-to-one mapping from the set of values of these parameters to an element of the group, which may denote as G, x1, x2, etc. up to xn. And in a simplified notation, we may write this mapping as the parameter x getting mapped to Gx. Now the set of possible values of these parameters form what is called the parameter space of the group. So this mapping is in fact a mapping from the parameter space onto the group. And the mapping is one-to-one as well. So given a set of values for the parameters, there is a unique element of the group corresponding to that. Now we will consider an example of a continuous group, another example of a continuous group, which is called a general linear group. And this is the set of all homogeneous linear transformations of n real variables. So that means we have n real variables denoted by y1, y2, etc. up to yn. and we consider linear transformations of. So starting from n real variables, we can consider a transformation to y1 dash etc. up to yn dash. Again, n real values. And this transformation is linear and homogeneous. So in general, it could be written in the following way: y1 dash etc. up to yn dash is equal to the sum matrix a11 etc. up to a1n, an1 etc. up to ann, multiplying y1 etc. up to yn. So the set of a linear transformation, a homogeneous linear transformation of n real variables can in fact be represented in terms of an n by n square matrix with real entries. So we would say that the set of all homogeneous linear transformations of n real variables, which we denote by GL n comma R, and they form a group and is isomorphic to the set of or the group of all n by n non-singular matrices under matrix multiplication. So GL n comma R, which is a general linear group involving n linear transformations of n real variables, is isomorphic to a set of matrices n by n real matrices with determinant not equal to 0. Now each such matrix A is n by n and therefore has n square elements, all of them real. The only restriction is that determinant of the matrix A is not equal to 0. And these elements can take all possible values over a continuous range subject only to this restriction, that their determinant is not 0. And therefore there are n square real parameters corresponding to this group. So the order of the group, order of GL n comma R, is n square. We will now consider what are called topological groups. We consider a continuous group G whose parameter space is a subset of an R-dimensional inner product space S. So we have a continuous group and its parameter space involving the continuous parameters is a subset of an R-dimensional inner product space. That means it's a space on which an inner product is defined. For example, it could be a subspace of Rn, the n-dimensional real space. Now, since S is an inner product space, it will have a norm defined by the inner product, and we can use this norm to define the continuity of the maps. And this is done by first defining what are called the epsilon neighborhoods of the group elements. So, as we have seen earlier, we have a parameter space and then we have the group. Then corresponding to every element, every point in the parameter space, there will be a group element. So if this is X, this is Gx. So let me rewrite. This is X and this is Gx. Now we can consider a neighborhood of the point x in the parameter space. This is the point x. Let me denote it by, this is x. And this is a neighborhood of x in the parameters. And remember, the parameter space has an inner product, and therefore a distance is distance function is defined there. Okay, so I can consider the set of points in the parameter space which we denote by y, such that y minus x, the distance of y minus x is less than epsilon. Okay, so we are considering the parameter space, and in the parameter space we consider a point x, and which is mapped to the group element gx. Now we consider the set of elements in the parameter space which are within a distance of epsilon of x, which may be denoted by writing this condition, that the norm or the distance of a point y from x is less than epsilon. So you consider all such points in the parameter space y which is at lesser distance than epsilon from x. Then each of those y will correspond to group elements gy, and we can collect all those elements gy's, okay, and the set of all those gy's form what is called the epsilon neighborhood of gx. So to repeat it once more, the epsilon neighborhood z epsilon of gx is the set of group elements gy, where y is the parameter corresponding to that element, such that the point y in the parameter space has the property that the distance of y from x is less than epsilon. Now we can consider the group composition. Consider two elements gx and gy, and the group composition actually can be considered as a mapping from the set of elements gx and gy to the element which is given by the product gx gy, or the composition gx gy of g. So in general we could consider this to be a mapping from the Cartesian product of g with g to the group G itself. So this is a map from this ordered pair gx gy onto the element gx gy. And similarly, the inversion is also a map, but this is a map from the group to itself. So given an element gx, the inversion map takes gx to the inverse of gx. Okay. Now, as I have discussed here, we could define neighborhoods for the group elements gx via this method, and this can in fact be used to define the continuity of the maps corresponding to the composition and inversion. But to do this, we consider first the composition map. So first let me remove this picture. Suppose we have two elements of the group which are gx and gy and they gets mapped to the product gx gy under the composition map. Okay. So what we can do now is fix an element gy. So given an element gy of the group, then this can be considered as a mapping from this first element gx to the product gx gy. having fixed gy to a particular element. Then the continuity of this map with respect to gx at that particular element gx is defined in the following way. Consider an epsilon neighborhood of this product element gx gy. Suppose gx gy is this element and gx is this and gy is this. Gx is this, gy is this, and this is the product gx gy. Let us call this as gz. So gx gy is gz. So we are fixing gy, and then this correspond to the composition correspond to a mapping from gx to gz. And we are looking at how we can define the continuity of this map at a particular point gx. Point gx means particular element gx with respect to this argument, the first argument gx. So we first consider an epsilon neighborhood of this element gz. Remember, gz is simply the product gx gy. So we consider an epsilon neighborhood of this. So that means the set of elements, the group elements such that the set of elements of say y, the set of elements gy such that y minus z distance is less than x, and that is this neighborhood, which we call as z epsilon of gz. In fact, gz is gx gy. Okay, so this is z epsilon of gz, which is gx gy. Then the continuity of the map, this map implies that given any epsilon, there epsilon greater than 0, there exists a delta greater than 0 such that we can consider a delta neighborhood of gx. So this is z delta of gx such that under this composition map, all elements within this z delta of gx gets mapped to z epsilon of gx gy. So that means all points that are close to gx here in this sense is mapped to the points close to gz again in this sense. So the definition of an epsilon neighborhood in terms of the topology of the parameter space gives us a way of defining the continuity of the composition map over here, because we can now talk in terms of epsilon neighborhoods. And since this composition map is a map from an ordered pair of elements to a group element, we can think of continuity of this map with respect to each of those elements. We can think of continuity with respect to the first argument or with respect to the second argument. So what we have done here is we fixed the second argument, then we considered continuity of this map with respect to the first argument, that is gx. So at that particular element gx, this map is said to be continuous if for every epsilon greater than 0, there exists a delta greater than 0 such that all elements that are in the delta neighborhood of gx gets mapped to the epsilon neighborhood of gz. So all elements in z delta gx gets mapped to elements in z epsilon gz, which is gx gy. All this while fixing gy. In a similar fashion, we can fix gx, and then the composition map will now be a map from gy to the product gx gy. Then we can define the continuity of the map with respect to gy at the point gy. So that means for every epsilon greater than 0, there exists a delta greater than 0 such that for all gz in z delta gy, the composition gxgz, that is the product, gets mapped to z epsilon gxgy. So the product or the composition gets mapped to the epsilon neighborhood of the product gxgy. In a similar fashion, we can consider the inversion map, which is a map from the group to itself. In terms of these epsilon neighborhoods, we can define the continuity of those maps as well. And a continuous map, a continuous group in which the composition and inverse are continuous maps in all group elements is called a topological group. So that means consider the composition map given by this. So from an ordered pair of group elements to another group element. So if this map is continuous both in the first argument and in the second argument, and the inversion map is also continuous, then such a group is called a topological group. We now discuss what are called connected groups. Now consider the parameter space of a group. So something like this. Now consider any 2 points, say denoted by A and B, or maybe X and Y. Now this parameter space is said to be connected if there exists a path lying entirely in the parameter space that connects these 2 points. Now you can see that there is a path that connects X to Y here. Whereas if the parameter space was something like this, it consists of 2 disjoint sets, and if X was this and Y was this, there is no path connecting X to Y which lies entirely in the parameter space. If there is a path like this that connects X to Y, then this part of the path is lying outside the parameter space. Now, the parameter space is said to be connected if for any 2 points X and Y in it, there exists a path lying entirely in it connecting X and Y. And this should be true for any points in X and Y. For example, even when we consider a disjoint set, a union of disjoint sets like this, we can consider 2 points X and X dash here in the first segment. They are connected. There is a path connecting them that lies entirely here. But, if we consider another point over here, then there is no path connecting X to a point like this and lying entirely within the parameter space. And therefore, this parameter space is not connected. Now, a topological group is said to be connected if its parameter space is connected. And now we can add qualifiers to the connectedness of the parameter space. And space is said to be k-fold connected if there exist k distinct paths that cannot be deformed into each other by continuous transformations that connects given 2 points on it. So the space is said to be simply connected if there exists only one distinct such path. If there exists k distinct paths, then it will be called k-fold connected. Now, a topological group is said to be compact if its parameter space is closed and bounded. By bounded, we mean the values of the parameter should be, the absolute values of the parameter should be less than or equal to maximum value. And the parameter space should also be closed. In that case, a topological group is said to be compact group. Now, a parameter space of an n-parameter topological group of order R consists of R continuous parameters and n minus R discrete parameters. It takes a discrete set of values. And the parameter space will contain a disjoint sets, each of dimension r if r is less than n. And one of these disjoint pieces contains the identity element of the group. And there will be one-to-one correspondence between elements of these disjoint pieces. And therefore, we only need to study the properties of one of those pieces. And it is ideal to study the disjoint piece containing the identity of the group. And since there is one-to-one correspondence between different disjoint pieces, we can get the properties of other pieces from one of them, the one that we have studied. We now discuss representations of continuous groups. Consider the elements Gx of a group G, where X is the set of parameter values and Gx is the corresponding group element. Suppose each of these group element Gx be mapped to a particular matrix which we denote by, say, G of X. So given a group element G of X, we map it to a matrix, a non-singular square matrix gamma Gx. So there will be one such matrix for each of the group elements. Now this mapping, which we denote as gamma from Gx to gamma Gx, if this is a homomorphism, that is gamma Gx times gamma Gy is equal to gamma Gx Gy, then this mapping is said to be a representation of the group G. So once more, if every element Gx of a group G is mapped to a set of non-singular square matrices gamma Gx such that this mapping is a homomorphism, then this mapping is said to be a representation of G. Now, so the group element X is mapped to gamma Gx. Now, if we consider it as a mapping from the parameter space, we see that given a point in the parameter space, this gets mapped to a group element Gx, and this group element gets mapped to gamma. So this implicitly defines a map from X to gamma Gx. So this map may also be represented as the symbol gamma from point in the parameter space onto gamma Gx. Now X is the parameter space and gamma Gx is the space of matrices, non-singular square matrices of a given point. And we can define the continuity of these maps. And if this map, which takes a particular point in the parameter space to a given non-singular square matrix gamma Gx, if that map is a continuous map, then gamma is said to be a continuous representation of G. So this mapping is a representation of the group provided the map is a homomorphism. And if the implicit mapping that is defined by this, which is a mapping from the parameter space to the set of these matrices, that is from a given point X in the parameter space to a matrix gamma Gx. If that mapping is continuous, then the representation is called a continuous representation of the group. Now, continuous representations of compact continuous groups satisfy some very important properties. Any representation of such groups is equivalent to a unitary representation. Remember the properties of representations of finite groups. Any representation is equivalent to a unitary representation by an appropriate similarity transformation. And the similar result over here is that given a compact continuous group and a continuous representation of that, any such representation is equivalent to a unitary representation. Now, any unitary representation is completely reducible. Remember, in the case of discrete groups also, all unitary representations, all reducible unitary representations were completely reducible. Similarly, over here, any unitary representation of compact continuous groups are completely reducible. Now, any irreducible representation of such groups is finite dimensional. Even though the group is infinite dimensional, any irreducible representation of compact continuous groups are finite dimensional. Remember, we are stating these properties without proofs. We now consider what are called Lie groups. Consider a topological group G with n parameters, out of which R are continuous parameters. As we have already discussed, the parameter space will be a collection of disjoint sets, disjoint pieces. And one of those disjoint pieces will contain the identity of the group. Now we consider a neighborhood n of the identity of the group. Now this will be a connected piece, and in that piece we only need R continuous parameters to discuss various group elements, because we are restricting ourselves to that particular connected piece. Now for any two elements, say Gx and Gy, in this neighborhood n, we also assume that the composition Gx, Gy of those two elements also lie within n. So we are restricting ourselves to a neighborhood of the identity of the group, and we are also restricting ourselves to the elements of this neighborhood, such that if Gx and Gy are two elements in this neighborhood, their composition also lies within this neighborhood. So Gx, Gy, let the element be denoted by Z. So the parameters of Gz are Z1, etc. up to Zr. As I have already said, we only need Z continuous parameters to be specified to identify this element in this particular piece n, which contains the identity. And similarly, this set of parameters are given by x1, etc. up to xr, and this one by y1, y2, etc. up to yr. So this composition map, which takes these two elements Gx and Gy and takes it to Gz, is actually a mapping between the parameter values x1, x2, etc. up to xr, y1, y2, etc. up to yr, to the parameters z1, z2, etc. up to zr. So in general, we may write the parameter zi as function zi of x1, x2 up to xr, comma y1, y2, etc. up to yr, and this is for all values of I running from 1 to r. And similarly, we can think of the inverses. So if given an element Gx, its inverse will be given by Gx inverse. This is also an element of the group. We assume that this is also in this neighborhood n. So this will be given by, say, another element Gx dash. So the parameters of the inverse are x dash 1, etc. up to x dash r, and the parameters of Gx are x1, etc. up to xr. So this inverse mapping actually defines a mapping from the set of values x1 etc. up to xr to the set of parameter values x1 dash etc. up to xr dash. So this may be defined as sorry, in this notes I have, instead of x dash I wrote z dash. Let me do that over here. So this is z1 dash etc. up to zr dash. So this parameters z dash I is a function of x1, x2 etc. up to xr. So we see that the composition and the inversion correspond to mappings between the parameters, and for the composition it is a mapping from the set of parameters x1 etc. up to xr, y1, y2 etc. up to yr to say z1, z2, z3 etc. up to zr. And for the inversion, it is a mapping from the set of parameter values x1 etc. up to xr to the set of values z-1, z-2 etc. up to z-r. So this defines set of maps. The composition and inversion defines the maps given by this and this. Now, if these maps, that is z-i is equal to this and zi is equal to this map, which are functions of this many variables, and this one is a function of this many variables. If these maps are analytic functions, then the group is said to be a Lie group. So let us formalize its definition. If there exists a neighborhood n of the identity of the group such that for all elements gx, gy in this neighborhood, for which the composition gx, gy is equal to gz is also an element of the neighborhood, and for all elements gx in G for which the inversion gx inverse is equal to gz dash, which is also an element of this neighborhood, the functions zi, which is defined by this map, and z dash I, which is given by this inversion map, if they are analytic functions of x1 etc. up to xr, and zi are analytic functions of x1 etc. up to xr, y1, y2 etc. up to yr, then the group is called a Lie group of dimension r. So we have a continuous group first of all, and it has r continuous parameters. So the order of the group is r. Order of the continuous group is r. And contrast it with the definition for the order of a discrete group. It is a number of elements of the group in the case of a discrete group. Here, the order of a continuous group is the number of continuous parameters of the group. Now, if we have a continuous group with r parameters, we consider a connected piece of the group which contains the identity element, and for all elements in that connected neighborhood of the identity such that their composition also lies within that neighborhood and the inverses also lies within the neighborhood, the composition map and the inversion map as functions of the parameters, if they are analytic, then such a group is called a Lie group of dimension r. Now we consider what are called the generators of Lie groups. Now, the continuous parameters are r in number for an r dimensional Lie group, and we denote them by x1 etc. up to xr. And let us choose these continuous parameters such that the parameters for the identity of the group is simply 0, 0, 0 and 0 for all r parameters. So xi equal to 0 for all I running from 1 to r, and this correspond to the identity. So G 0, 0, etc. up to 0 is equal to the identity of the group. And we now consider a continuous representation which we denote by this symbol G of the group in some vector space V. So obviously these objects Gx are linear operators in that vector space, may be represented by matrices. So we would say that Gx is isomorphic to these elements, the representation elements Gx. So obviously the identity is represented by the identity operator. So G, the linear operator corresponding to the identity element, and that correspond to the parameter value 0 for all xi's, and that will be equal to the identity operator. Now we consider elements that are close to the identity of the group. So the parameters will also be close to the parameters of the identity. And we consider one case in which the xjth parameter is equal to epsilon j, which is actually an infinitesimally small number, and all xi is equal to 0 for I not equal to j. So that means we have a parameter value given by 0 for x1, etc. up to xj minus 1. Then xj is equal to epsilon j, where epsilon j is infinitesimally small. Then all other parameter values are 0. Now this mapping from the parameter to the representation operators is a continuous one. And therefore, we may write, and we also know that these are analytic functions. So therefore, we may write this as G0, then epsilon j, and all other parameters 0 is very close to the operator for, the linear operator for the identity, which is the identity operator. So identity operator plus a small an operator that has effect very small, or in other words some operator that is multiplied by a very small number, and we take that number to be epsilon j. So we will expect this to be proportional to epsilon j when epsilon j is very small, and the other parameters will be of order epsilon j square. The other terms in this expansion will be of order epsilon j square. So I may write this as 1 plus I epsilon j plus times ij plus terms that are of order epsilon j square. And this operator ij that appears here is called the generator of the Lie group corresponding to the parameter xj, because this appears when we vary from, or we move from the identity group, the identity of the group with the parameter xj is only varying slightly, infinitesimally a small amount from the parameter values of the identity of the group. Now, since there are r parameters, we can define r such generators, one corresponding to each of these parameters. And from this, we can easily see that if I take G 0, then epsilon j, then 0 minus this identity, okay, I take this to the left, which is nothing but G 0 for all values of the parameters, that would be equal to I epsilon j ij plus order of epsilon square terms. Now I take epsilon j tend to 0, and therefore I may neglect the other terms, or in other words, keeping that, this would be order of epsilon j square, And if I divide it with say I epsilon j, I will get 1 by I epsilon j of g of 0 0 epsilon j 0 minus g 0 0 0 equal to ij divided by I epsilon j. But then this will be of the order of, this term will be of the order of epsilon j. Now take the limit epsilon j tend to 0. Take the limit on the right hand side. This does not depend upon epsilon j and therefore this remains ij. But this is of order epsilon j, and as epsilon j tend to 0, this tend to 0. So we see that limit epsilon j tend to 0, 1 by epsilon j of this term is simply ij. So the generator ij can be calculated using this formula. Limit epsilon j tend to 0, 1 by epsilon ij, and this minus that. Now, we may also be able to choose parameters in such a way that G00 AJ00 times G00 BJ 00 equal to G00 AJ plus BJ 00. So that means if we only change the parameter xj, so we have G AJ times G BJ, and that will be equal to GAJ plus BJ. So if we can choose parameters in such a way, that means, by the way, all these equations were written for infinitesimal changes from the identity element. Now we can do the following. Suppose, we keep all parameters except xj as 0. Now we are only changing xj. And I want to find out an expression for the element corresponding to a finite value, say for example xj for the jth parameter. If xj was infinitesimally small, I could use this. In terms of the generator, I can write this as this equation. However, when this is finite, what can I do? So this is where I assume that I am able to find the parameters in such a way that this satisfy this condition. That is, while taking the composition, the parameter values simply adds up. Remember the very first example, R is at phi 1, R is at phi 2 was equal to R is at of phi 1 plus phi 2. So here, this satisfies exactly this condition. So it demonstrates that it is possible, it may be possible in some cases that we can choose our parameter values to satisfy this condition. So in that case, I can write this as, so I can, for example, consider the following product. I will consider G, by suppressing all 0 values, I will only consider xj. Okay, now, so this will be now for simplicity denoted by xj. Now I may write this as G xj by 2 into G xj by 2. But because of this property that the parameters adds up, this should be equal to G xj by 2 plus xj, that is xj. But now if I write xj by 3 and one more xj by 3, this should again be equal to gxj. But instead, if I write as gxj by n, gxj by n, gxj by n and take the product n times, that is, if I take the following product, phi j running from 1 to n, or maybe so L running from 1 to n, G xj by n. So that is a product of n terms of this. So the parameter corresponding to this product will be sum of these parameters. There are n of them. So n into xj by n, which is xj. But now I can take the limit n tend to infinity here. Okay. So I will take this product. There will be infinity number of terms here. But now as n tend to infinity, this quantity xj by n, that goes to 0, which is infinitesimally small. Then I can write this in terms of the generator. So something similar to this. So I may write this as each of this term as identity plus I, instead of epsilon j, I have xj by n times. There are other terms of order 2 in xj by n. But since I take n tend to infinity, xj by 10 to 0, and I may neglect them. Then this is a mistake. I don't have to put n here. So then this can be written as limit n tend to infinity, the product L running from 1 to n. Then 1 plus each of this term is written by 1 plus I xj by n ij. Remember, none of these has a dependence on L, but this is a product of n terms like this. So this product can be written as 1 plus I xj by n ij to the power with limit n tend to infinity. But there is an algebraic identity which says that something like this is equivalent to the power series for e to the power I xj ij, where this exponential is now defined in terms of the power series, which is sum over n running from 0 to maybe m running from 0 to infinity, sorry, e to the power, yeah, m running to the infinity I xj ij to the power m divided by m factorial. This is the power series expansion for the exponential function of real variable, for example. So the same power series correspond to this algebraic identity. Here, remember, ij's are operators. So the product of operators is defined. Therefore, the powers of operators is defined, and the sum of them is also defined. Sum of operators is also defined. So we see that for a finite value of the parameter xj, now since it is a Lie group, we can write this as g corresponding to xj is simply given by exponential I xj ij. Remember, here we have only varied the j parameter xj. Now, if all parameters are varied for g, x1, etc. up to xr, this formula gets generalized to this one, where instead of xj ij, we need to take the sum over j running from 1 to r xj ij, and there is this exponential factor also is there. Now, if g is a unitary representation, then we can show that the generators are self-adjoint. Okay. So to see this, we consider an infinitesimal transformation. Say gx. Okay. Here we assume that only the jth parameter is changing from 0. Okay. So I consider an infinitesimal transformation. So g epsilon j, which will be 1 plus I epsilon j times ij. Now, its adjoint would be g dagger epsilon j would be since this is a sum of operators, the adjoint of sum of operators is sum of the adjoint. So one dagger, the identity dagger is identity. One, then take the adjoint of this, I changes to minus I, epsilon j is real, and therefore epsilon j, then the adjoint of ij, so ij dagger. Now G is unitary because it's a unitary representation. That's what we have assumed. So in that case, G dagger epsilon j times G epsilon j should be identity up to first order, because in this expression, I mean, in general, it should be equal to the identity operator. But since we are restricting ourselves to terms up to first order in epsilon j, if we substitute for G epsilon j using these formulae, then we expect this product to be equal to identity operator only up to terms of order 1 in epsilon j. So to see this, we substitute this over here. So what is G dagger epsilon j? That is 1 plus epsilon ij, sorry, epsilon j ij times G dagger. So yeah, so this is what I can also take G times G dagger, and that's what I have done in these notes. So let me do that. So G is 1 plus epsilon j ij times G dagger is 1 minus I epsilon j ij dagger. That is this. And this should be equal to 1 up to order 1 in epsilon j. And that's why I use this symbol. Now I can take the product 1 times 1. Identity times identity is identity. Then first order term in epsilon j. There is a term which is coming from this product, which is I epsilon j times ij times identity is ij. Now there is one more term which is of the order of epsilon j, that is coming from this product. So 1 times minus epsilon ij minus I epsilon j times I dagger j. So collecting those terms, I will get 1 identity plus I epsilon j times ij minus I dagger j. Then there will be other terms of order epsilon square, which we neglect because we are only interested in terms up to order 1 in epsilon j. And the right hand side, it should be equal to identity. That is true only if this is 0. So that means ij minus I dagger j should be equal to 0, or in other words, ij should be equal to I dagger j, which means the generators of a unitary representation of a Lie group are self-adjoint.